it's impossible for Wayve and many companies in the AV space, once they reach a certain level of maturity, to go test the vehicle in the real world. So why GAIA-4? Why world models? Why simulation in general? It's to evaluate the vehicle densely across scenarios around the entire world, but doing it within the confines of an offline testing tool.
All right, so today I'm excited for our new editor, Ben Hubbard, to take the interviewer's seat for the first time on the podcast. Ben has spent the past 6 years covering the sustainable mobility sector, reporting on everything from autonomous vehicles and delivery robots to drones, eVTOLs, and the wider mobility ecosystem. You might have seen his writing over on the Driverless Digest, so I'm excited to present this interview today that Ben is going to host. And in this episode, he's going to be speaking with Wayve's Vice President of Engineering, Brandon Basso, about their new generation world model, GAIA-4, and how AI is shaping the next era of autonomous driving. All right, let's hear from Ben.
Brandon Basso leads Wayve's simulation, data, evaluation, and validation systems, which are central to measuring the performance and safety of Wayve's autonomous driving technology as it scales across global markets. Brandon brings more than a decade of experience delivering safety-critical AI and robotic systems in real-world environments. He previously held senior leadership roles at Cruise and General Motors, where he supported the commercial deployment of driverless robotaxi services across multiple US cities. Brandon, how are you doing today?
Doing well. Thanks so much for having me, Ben.
No worries. Thank you. Thanks for coming on the podcast. I must say your name has got a very nice ring to it, with the alliteration on B.
Yeah, thanks. It alliterates. Thanks to my parents.
So obviously Wayve is a big name in the AV industry. But before we kind of get into this research report that you just launched, I would love to kind of understand a little bit more about your day-to-day role and what that looks like.
Yeah, absolutely. Well, you covered my bio well. Day to day, I'm involved in the simulation and offline test and validation of the AI driver. This involves working directly with all the people, all the fantastic engineers, product managers, operations folks who help build that stack and especially test it offline. So in some ways, it looks like a standard management role, but Wayve is a very unique company. So there's a lot of nuance and technical direction, and working with the teams directly involved in the day-to-day.
Thank you. For someone who's new to Wayve, what actually is the Wayve AI driver?
Yeah, so the Wayve AI driver is also called the autonomy stack. It is the collection of software and models that allow the vehicle to operate on public roads around the world. So not just in the UK, not just in Tokyo, but in many markets throughout the world. And it is the thing that outputs all of the driving actions. It takes in all the sensor data, radar, camera, etc., and it outputs the driving actions in the form of steering and braking, and it makes all the real-time decisions about how to behave in comfortable, safe, and legally compliant ways, depending on the market that it's in.
You've been building generative AI world models since 2018, right? So I believe you call them GAIAs. What is a world model, and why is it useful for teaching an AI how to drive?
Yeah, and to clarify, I'm in charge of the world modeling side, not the AI driver side. There's a very talented team that's behind that at Wayve. But roughly speaking, world models in the industry are networks that predict the future actions of the world, as opposed to predicting the actions of how a car should drive. So it's everything around the car that is evolving. This includes all of the vehicles in the scene, all of the people, all of the background objects that might affect the driving. And it's a model that fundamentally understands physics and how the world behaves, as opposed to how the ego vehicle, the AI driver, should behave. And this is a super challenging problem. It's a hot topic in research today. It's one of our largest models at Wayve, Gaia, the one that you mentioned, and one that we've recently launched our 4th generation of, and that's GAIA-4.
So with these world models, like what's the end result? What's the final problem that you're trying to solve with it?
Yeah. So the wonderful thing about working on this particular aspect of simulation and evaluation and validation is you can go see the output. So if you go check out the blog post that we recently put up, you can see what the output is. But I think the spirit of your question is, well, why? Why is it useful? And the crux of it is this: it's impossible for Wayve and many companies in the AV space, once they reach a certain level of maturity, to go test the vehicle in the real world. It's expensive to do so. In some cases, it's risky to do so, especially if you're trying to test the vehicle at the limits of performance. And also, it's just impossible to collect all the data that you need to either train the vehicle or evaluate it against all the scenarios it needs to see. So why GAIA-4? Why world models? Why simulation in general? It's to evaluate the vehicle densely across scenarios around the entire world, but doing it within the confines of an offline testing tool.
So you're trying to get an exact replica of a real world situation and working out all of the intricacies, yeah, and all of the blind spots, all of the edge cases, and wrapping that up into one singular model.
Yeah, I mean, exact replica is it can be really nuanced. What we're trying to do is capture all of the nuance in the world, literally all of the nuance, how reflections work, how a vehicle behaves around puddles and potholes, how cyclists behave in Tokyo versus London, all of that nuance, all of that rich detail, and generate plausible situations. Sometimes we call them counterfactuals. If we started from a real world scenario and we're trying to generate what other things could have happened, we can also generate scenarios in a novel way from scratch. But yeah, we're trying to capture all of the nuance in as real of a way as possible, plausible way as possible of how the world could have evolved. So in that sense, it's quite literally a world prediction engine where it's trying to figure out the ways in which the world can evolve. In some cases, we try and do that in a very, very, very constrained way. For example, the blog post goes into this. We have a mode that we can run Gaia in called World on Rails, which basically takes exactly what happened in the real world, changes it 0, that's the goal, and allows us to evaluate new software against a world that we can interact with, but is largely static with respect to how we recorded it previously.
Before we get into the Gaia new model, we've seen Waymo struggling in floods. We've seen the 4th of July incident in San Francisco. Are there kind of certain situations where no matter how much simulation you have, you just can't predict human behavior in edge cases?
I think I would like to say never say never, that it's not it's not something that's unsolvable. But yeah, it is really hard to predict all of those situations, and really you're trying to predict the joints of how the world evolves in complex ways and how the vehicle interacts with it, and that really is the task of simulation. Gaia gets better every day as we feed it more data and rich data throughout the world. And one of the core concepts that we have is, if we can feed it enough data, if we can run it performantly, that's a huge mandate that we have, to be able to run it performantly, i.e. low cost and fast enough. We can capture all of the important richness of the world, especially around these rare and critical situations like the ones that you alluded to, and we can reliably test the vehicle in those ways. We can't do all of that today, but that's the goal.
How far off do you think we are?
Oh, well, that is a very hard question to answer. And the signal that we look at to answer it is what we call escapes. Common topic in software engineering in general, which is essentially how often are you surprised by how your software model behaves when subject to real conditions. So what we look at is, how often are we surprised? How often do we learn something from the real world? the great thing about a Gaia and a sort of fundamentally ML world modeling based simulator is as soon as we see an escape, we can use that as training data to improve the model. But we are generally, the very, very general answer, generally completely unsurprised by things that we see all the time in the markets that we drive in. And then two areas where we have to get data to learn is areas we've never seen before, and people in vehicles behaving in ways that we haven't seen before, although we do have a lot of that in our training data. I'll give you a concrete example. A lot of the recent work in GAIA-4 was improving how we drive on test tracks, because it's very important for us to go drive on test tracks. Well, as it turns out, we have 1,000,000x more data for driving in the real world than driving on test tracks, right? So that's one area where we need to improve how the simulator predicts the world and behaves, because test tracks, in fact, are a fairly novel scenario. You and I have probably never driven on one, for example. So they look different.
Never been on one.
Yeah, so that's like one of these nuances that's sort of non-obvious until you see it, that it's an area where you need data in order for the model to correctly predict the world. How far are we? Hard to say. But generally speaking, for the most common scenarios that we see on the road and the most common critical scenarios, we have a lot of data around those and can generally correctly predict how they would have evolved or could have evolved under different circumstances.
Great, thank you. Let's get on to GAIA-4 then. So you've just released this new generation, this new model. This is a big milestone for Wayve. Correct me if I'm wrong. What does it allow you to do that wasn't possible before?
Yeah, couple key things. There's many in the blog post, but I'll drill into two. One of them is closed loop, and then the other is multimodality, different sensors. So the first one, closed loop versus open loop. There's a nice picture that explains it a little bit better, but really in self-driving cars, autonomous vehicles, and robotics in general, you have two ways of evaluating a system offline. You have something called open loop, which is replaying pre-recorded data through a new version of the software or the model and seeing what the outputs are. So that's called open loop. Closed loop, which is the advancement with Gaia, is replaying that real world data through the autonomy stack and then taking the actions that the simulated autonomous vehicle does, the AI driver, and feeding that back into the world model and saying, well, how does the world evolve as a result of these actions? Now, that's kind of a mind-blowing thing to think that you could predict, for example. So that says in simulation, if the car, the AI driver decides to slow down, we should expect to see the view in the simulation to reflect slowing down. You should see the camera view from a different vantage point, and we'll get to this in a second. You should also see the radar returns from a different vantage point. If you slow down or if you speed up, you should expect to see perhaps the other actors react to you differently. And we talk about different modes of interaction we could put Gaia in. We mentioned world on rails. There's also one that we can do with reactive agents, which is another one of the advancements mentioned in the GAIA-4 post. So closed loop is actually absolutely critical to our offline test capability, because it's how, when you and I go drive, it's how we experience the world. When we drive a certain way, when we slow down or speed up or take a left-hand turn versus a right-hand turn, we see different stuff, and we feed that back into our sensors, our eyes, primarily, and we drive differently. So closing the loop is a huge, huge advancement for Gaia and for these class of world models in general. It is a thing that the industry has been able to do for a while, to be clear, but with very different styles of simulation. These are more procedural simulators, rendering-based simulators, game engine-style simulators. There's, the industry going back to as long as I've been in it has been able to do closed-loop simulation. This is a specific advancement about us being able to do it with a world model. So that's one. The second one I'll touch on briefly. I talked about reactive agents. The second one is multimodality, so different sensors. So if you go look at the Wayve vehicles, if you go look at other L2, L2 plus systems out there, and especially on up to L4 systems, you'll notice they have more than just cameras on them. And it's incredibly critical that we're able to simulate those sensors. So the big advancement that we mentioned in Gaia is our ability to simulate radar. I'll also note that radar is a notoriously hard thing to model and simulate for procedural simulators. If you think about the physics models that would go into simulating how radar works, it's very complex. So us being able to do that inside of a single model and have those returns overlaid with the camera information, as you can see in the blog post, we have some nice videos on it, is huge. And even more important, that actually the end goal is, does it matter? Do we see differences in performance in simulation? And we have a nice example in the post showing where we do.
Yeah, can we go back to the closed loop simulation? So can you give us like an example? So say if somebody was driving down the road and a deer jumped out, and can you give us an analogy of like what the model could do previously in that situation and what the model can do now with the closed loop? So you're saying that the closed loop, it can kind of see all of the actions past the point of the deer jumping into the road. How did everyone react after that event? Is that right?
Yeah, the way I would describe it is that it models how the world evolves due to the actions of the autonomous vehicle and how the autonomous vehicle, the AI driver, sees things from a different perspective due to how the world evolved and then feeds that signal back into the driving model. It's exactly how you and I drive is the best way to explain it, which is if we make different choices, we see the world from different places and different vantage points, and then we react to those new vantage points. So closing the loop quite literally means taking those new vantage points that we see and feeding that back into the driving model so that we can have a consistent simulation cycle over cycle. It's useful to think about what it looks like in a non-closed loop fashion. And what that looks like is that the model, the AI driver now I'm talking about, does not see the new vantage point of the sensor data. So it does not necessarily react how you would react from the real world. What we call this in the open loop world is a consistency issue or a divergence issue. And to make it clear, we use open loop simulation all the time. It's incredibly valuable. It's extremely cheap for us to run, and there is valuable signal that we can get out of it. But for highly dynamic situations where you would expect a very different action, or you want to explore how things could have evolved differently, you need closed loop simulation.
Great. Thank you. Thank you for clarifying that. I saw the diagram and it kind of made sense, but it makes so much more sense when someone explains it to you.
Yeah.
Can you talk about the difference between AV 1.0 and AV 2.0 and what's the main difference there and why does that kind of shift matter?
Yeah, I would love to. And I think I can speak to it because most of my career I've spent not working on AV 2.0. This is a recent thing for me. So AV 1.0 versus 2.0, this is the way that Wayve describes the difference in approaches, both philosophically and technically, to developing the driving stack. So if you think about in the limit, and by the way, this is a spectrum. So companies live anywhere on the spectrum, but to paint it in terms of the endpoints, AV 1.0 is defined by driving systems that largely have interpretable components and subcomponents that determine the output behavior of the vehicle. The input output is the same, sensor data in, driving policy out, trajectories out. But the intermediate is very different. In AV 1.0, you might have heard of perception systems. You might have even heard of prediction systems going way back when. And then there's planning systems or behavior systems. Lower level, there's even other subsystems, control systems, and then even low level like motor control systems, actuators. But AV 1.0, 2.0 is really focused on that trajectory out portion of the system. In 1.0, you have these separable components. They can either be learned or they can be analytical. In many cases, it's a mixture of both. And they have these boundaries that are human interpretable. So the output of a perception system is typically things like bounding boxes, objects like this is a pedestrian, this is the space it occupies. You might even have in a prediction system, a prediction of the future trajectory, and then the planning system outputs a trajectory or the behavior system. So that's AV 1.0. AV 1.0 has a lot of benefits, and it's also where the industry's been for a while. One of the benefits is you can directly interpret each individual component, and you can reason about it with human logic, like, is this a person or not? Is this bounding box correct or not? That's a huge benefit just for understanding, right? Okay, so clearly there's a reason for doing AB 2.0. AB 2.0 is Wayve's approach to developing autonomous vehicles, and it's specifically with an end-to-end model. So those intermediate subsystems don't exist inside of our model. There is no representation inside of the model explicitly for bounding boxes or perception. Why would you do such a thing? Well, it turns out that what we found over years and years of working on this is that it is extremely efficient to develop a single model that can reach very high levels of performance that works end to end. So quite literally, it is all the sensor data in, single trajectory out. The way that these models are trained and improved is by feeding in more data from the real world. And we do see huge performance increases in terms of the output performance with these classes of systems. One thing I really want to highlight about the difference between AB 1.0 and 2.0 is sometimes I think that interpretability and separability and that property of 1.0 systems is viewed as an intrinsic safety property. It is in fact not an intrinsic safety property. It just means that you can reason about it in different ways than you can a 2.0 system. There's many properties that we see of our system, in particular the safety outputs of the system, so that the outputs of the system, the heads of the model, that produce braking maneuvers in situations where hard braking is required. There are many cases where we see highly, highly advanced emergent safety properties of that system in cases where 1.0 systems struggle. So for example, temporary signage. Our system, because it does not rely on a pre-cached map, has no concept of a temporary sign or temporary traffic light versus a permanent one. It's all just a traffic light and a sign. We see failures like this in the industry all the time where, oh, that was a temporary sign, it was a construction zone, something highly dynamic. Our system does not distinguish between those, so it tends to behave very naturally and correctly as you and I would when these situations arrive that are not pre-cached in an offline map. And that's a safety property. That's an intrinsic property of the system where it understands the fundamental dynamics of the world and says, that's a traffic light just because it's not one hanging off a pole and it's hanging off this temporary thing in this construction site. It's one I still need to obey in the same way I would all the other traffic lights. So that's a very broad overview of the differences between 1.0 and 2.0 and one sort of emergent property that we see.
Can you share a little bit more about the performance increases that you're talking about? And what sort of scale are we talking about?
Yeah, so I'm speaking about those performance increases relative to Wayve and how we see the performance of our system increase cycle over cycle. Again, I want to caveat, I'm not the person who leads this effort at Wayve, but what we see, and this is a trend that is we see in frontier labs that work on large language models and lots of other areas, is that with our approach to learning, with our model architecture and with the single end-to-end model, that is, what we see is that we can feed the model data from where it is deficient, and we see direct improvement on the things that we want to improve on. There are no hard boundaries in the system where if a perception system flickers, the vehicle will hard brake, for example. No such boundary in the system. There's no such hard boundary in the system where if someone mislabeled a traffic light, the vehicle will blow through it. So the system just directly gets better from data. We measure performance in 4 different dimensions. One is safety, and very directly collision safety, but then also near miss. We measure compliance to traffic rules, and that's different in different geos. We measure a thing that we call comfort, which is probably the vaguest of all of them, but it's, you can broadly interpret it as your perception of how comfortable the ride is. I think we all have like an intuition for what this feels like. It's the difference between, a 1-star hailed ride versus a 5-star maybe sometimes matters a lot. And then we also measure other types of special classes of issues. But taken all together, what we see is that cycle over cycle, and we train models literally every day and we put them on the car, we're generally able to improve orders of magnitude year on year on our driving performance. We're not there yet, of course, but our systems, and hopefully we can get you in the car someday. I think you have been in the car, right?
I actually haven't, but Harry Campbell has.
Ah, that's right. Okay. Well, Ben, a formal invite. Hopefully, we can get you in the car someday. You can experience it directly, but what we do see is tremendous improvement, and we benchmark this against other players in L2. I'm not um, able to quote the exact performance statistics, but generally speaking, as the person who works on the evaluation side of things, it is impossible in a single ride or in a collection of rides over thousands of kilometers to see concerning issues. We generally have to find them in simulation because unless something has gone wrong, there's like a major issue or major bug, we generally don't see them in road driving anymore, which is as it should be, right? You should not, the definition of success here is the absence of issues in, in small numbers of miles and kilometers.
Yeah, I'm just thinking about rating the performance of a ride. And, you give the example of rating a ride after an Uber trip. And, you give it 3 stars, but why do you give it 3 stars? It could be so many different reasons. It could
Yeah.
be, because you went over a bump and it just felt a bit uneasy, or it could be something that the driver said to you that you didn't like, and trying to capture all of those different elements must be quite a challenge.
It is challenging. I think comfort is one of the hardest and most nuanced, and probably one of the most frontier problems for our industry in general, whether we're talking about L2 vehicles that you can go out and own. So these are owner operated vehicles like we see out on the road today, on up to robo taxis. It's the same issue. And it's not just about harsh brakes and swerves. It could be about really, really nuanced behavior. What was the site selected for a pickup and a drop off location? Did the vehicle pull into the parking spot you expected? Now, and these are things that we might not exactly be the same as comfort, but they're all part of the overall ride experience. They matter greatly to our partners, like our public partnerships with Uber. It's hugely important. It's quite core to their business. So it's something that we focus on. And the best part of the AI driver is, again, I'll return to the point, is it gets better with data. You give it data and it gets better at problems. And what we generally find is that for tasks that are really challenging to describe with a set of rules, that might be a more germane approach to self-driving development in AV 1.0. Describe to me in rules what a good parking spot is. Very hard to do. For problems like that, where you and I generally do it correctly, when you can feed the model data, in general, we see tremendous performance right out of the box, zero shot, simply because of the model this great property that we have that it learns directly from data.
What are some of the downsides to Wayve's AI model and approach? You obviously got this new model and you're backing it, but yeah, what are if you had to kind of scrutinize it and hold it account, what are some of the downsides?
Yeah, for sure. I mean, there's downsides on the development side that, like I mentioned, like the introspection property. So when something's going wrong, it's not as simple as saying, well, clearly, this pedestrian was misunderstood as, a signpost or something like that. Generally speaking, we have to be very deliberate and invest in introspection tools. And a lot of cases, those tools look like data mining tools and search tools for figuring out what exact data do we need to feed back to the model. What are the active learning loops that we need to make sure that we improve the failure modes that we see on the road? And again, Wayve has been doing this singular approach for 8 years now. So we've done a really good job of developing those sorts of tools. So that's on the driver's side. One thing we haven't really touched on yet is validation. So validation is the process of certifying a software release and saying, we think that this is exactly these performance statistics, and this is why we think it's okay to ship. And here's specifically why we think that. What is the credibility score for each of those measures, and why we think it's okay to ship. So it's a report and it's a stamp of certification. That is an extremely hard thing to do for an AV 2.0 system, and the thing that makes it challenging is that lots of these reports for in an AV 1.0 context say things like, well, here's exactly the rate with which stop signs or traffic lights are not obeyed or marginally obeyed. That's a very simple thing to measure in a system that knows where all the stoplights and traffic lights are. For us, that's a challenging problem, a challenging classification problem, because the system, again, has no such concept. It does not know specifically this is where this is in the world. That said, we are making a lot of progress on this problem, and I do think that the solution that we have here is more robust, again, because we treat it like a data problem. So we feed data into classifiers that classify performance. And the great thing that we see about these classifiers for, let's say, stop sign compliance is that they generalize really well across different geos. So stop sign compliance might be a very hard thing to write a rule about if you want that rule to be generic across the entire world. Where's the stop line? What's the norm in that geography? However, if we treat it like a learning problem and a classification problem, we see great generalization of that same classification task across different geographies. And this is part of a broader collection of approaches that we're referring to as validation 2.0, which is the next phase of validation. How do we treat the validation problem much more like a data problem and still provide these hard guarantees that the industry and our regulators demand?
Validation 2.0, when is that coming out?
Well, we're working on it right now, internal to the company. It's in fact the approach that Wayve has been on since the very beginning, but we'll have more to share soon on specifically the pillars of that approach. One thing I can share is absolutely central to that approach is Gaia and GAIA-4. Why? Because certain classes of events we have to simulate in closed loop, and of course we have to simulate with radar. There is a line somewhere in every validation case that says, here's how a vehicle performs when it's foggy out or in rain or at night when radar really does matter. And if we can't simulate that, and again, this is all predicated on the idea that these events are so rare, you're just never going to be able to drive enough real world miles to collect all the edge cases. You're never going to be able to do the hazard analysis in any sufficient way based on just real world data. Well, then what do? We have to be able to simulate those things. And we have to be able to simulate them with incredibly high fidelity. By that, I mean sensor fidelity and camera fidelity in order to have a credible claim at the end of the day that here's why you should trust this simulation of all of these highly nuanced events in the real world. So GAIA-4 in particular is absolutely central, one of several pillars of validation 2.0.
Brandon, thank you so much for such detailed explanation. It's been a real pleasure to talk to you. And I think we're going to have to wrap things up, but I really appreciate you coming on the podcast.
Absolutely. It was a pleasure, Ben. And hopefully we can get you in the car soon.